Welcome to The Explainer. Today, we're heading straight into the darkest objects in the cosmos to find the brightest answers. And our guide on this journey is physicist Brian Cox, who thinks black holes might just hold the key to, well, everything.
I mean, could black holes really be the key to understanding the entire universe? It sounds a little bit like science fiction, doesn't it? But according to Brian Cox, the answer is a huge yes. He says, forget thinking of them as just these giant cosmic vacuum cleaners. No. They're the ultimate laboratories for pushing our understanding of physics to the absolute limit. So, why? What makes them so special? Well, it's because black holes are basically a cosmic battleground. They're the one place in the entire universe where our two greatest theories of everything just break. You've got Einstein's general relativity on one side, that's the theory for big stuff, planets, galaxies, and on the other, you have quantum mechanics, the rules for the tiny, tiny subatomic world. And in a black hole, these two theories don't just disagree, they violently contradict each other. Cox says that if we can figure that out, that conflict, well, that's the key to a complete theory of reality. Okay, so to really wrap our heads around this puzzle, we actually need to rewind the clock, way back. We're talking long before anyone had even heard the name Einstein, to a surprisingly simple idea from the 18th century. That's right, believe it or not, the idea of a black hole is more than 200 years old. Way before we started talking about warped spacetime, a couple of thinkers, John Mitchell and Pierre-Simon Laplace, they came up with the same wild idea, completely independently. And it all boiled down to one single concept, escape velocity. And the idea that kicked this whole thing off is actually pretty easy to grasp. Just, picture throwing a ball up in the air. If you don't throw it very hard, gravity just pulls it right back down. But if you could throw it with enough oomph at exactly the right speed, that's its escape velocity, it would just keep going and never come back. It would break free from Earth's gravity forever. And that magic speed, it's all about how massive and dense something is. So to get away from Earth, you'd need to be going about 8 miles a second. To escape the massive gravity of our sun, you're looking at a mind-boggling 400 miles a second. So this got Mitchell and Laplace thinking. They asked this incredible revolutionary question: what if you had an object that was so massive and so incredibly dense that its escape velocity was faster than the ultimate speed limit in the universe, faster than the speed of light? And that thought experiment from way back when, it perfectly nails the modern idea of an event horizon. It's not some solid surface you could, bump into. It's a boundary, a point of no return in space-time itself. Once you cross that line, that's it. You're not coming back. But then Einstein came along, and his theories added this extra super weird twist. If you were watching something fall in from a safe distance, time for that object would seem to slow down, until it just freezes at the edge. And this leads to maybe the most mind-bending prediction from general relativity. Deep inside a black hole, the math just breaks. It predicts a singularity. But here's the crazy part. It's not a place in space. The warping of spacetime is so extreme that space and time literally swap roles. The singularity becomes a moment in time, an unavoidable future. For anything that falls in, it's the literal end of time itself. Now, for a long time, this singularity thing was just a mathematical monster that physicists kind of tried to sweep under the rug. But then, the real breakthrough happened. Stephen Hawking completely changed the game. He decided, okay, forget the unknowable center for a minute, let's look at the edge. He looked at the event horizon, and he brought the weird and wonderful rules of the quantum world into the picture. And Hawking's idea was just wow. It was absolutely revolutionary. See, he realized that in quantum mechanics, empty space isn't really empty. It's fizzing with these pairs of virtual particles that pop into existence and then immediately disappear. But, and here's the genius part, right at the razor's edge of a black hole's event horizon, one of these pairs can get split up. One particle falls in, gone forever, but its partner escapes out into the universe. And when it does, it becomes a real particle, carrying away a tiny, tiny bit of the black hole's energy with it. This led to a conclusion that just floored everybody. Black holes are not forever. They leak. Over these vast, unimaginable stretches of time, they lose energy through what we now call Hawking radiation. They slowly, very, very slowly evaporate until one day there's just nothing left. They aren't eternal prisons after all. They die. But this incredible discovery, the idea that black holes can just fade away, well, it created an even bigger problem, a much deeper one. In fact, It led straight to one of the most famous paradoxes in all of modern physics, a puzzle that has kept scientists up at night for almost 50 years.
Just think about it for a second. You have a giant star, it collapses, and boom, you get a black hole. For billions of years, it just gobbles up everything that wanders too close. Planets, dust, asteroids, you name it. And then, after all that, it just evaporates into this random, featureless heat glow. So, where did all the stuff that fell in go? What happened to the information that made up a planet or a star? To get why this is such a huge problem, Brian Cox has this perfect analogy. He says, look, imagine you take a book and you set it on fire. According to the laws of physics, information can't actually be destroyed. So in principle, if you were able to collect every single atom of ash and smoke and every bit of heat that came off that fire, you could piece it all back together and reconstruct the book. The information is scrambled, sure, but it's not gone. That's a fundamental law of our universe.
And that is the heart of the paradox. Hawking's original math seemed to show that the radiation coming out of a black hole was completely random. It had zero information about what fell in. So it wasn't just scrambling the information from that book, it was acting like a cosmic shredder, permanently deleting it from existence. And that breaks one of the most sacred rules of quantum mechanics. It's a fundamental contradiction right at the core of our understanding of the universe. So what do? How do you solve a paradox that puts your two best theories of the universe in a head-to-head cage match? Well, the answer, and physicists are still hammering this out, is forcing us to let go of some of our most basic ideas about reality itself. So, where do things stand now? Well, after decades of fierce debate, the general consensus is quantum mechanics wins. No information is actually lost. That book you threw in, it's not destroyed. Its story is still there, somehow encoded in that faint glow of Hawking radiation, just in an unbelievably complex, scrambled-up way. Okay, but for that information to get out, something big has to give. Our everyday picture of a smooth, continuous reality, it has to be wrong. And this leads to an absolutely staggering conclusion. The very space you're in, and the time that's ticking by for you right now, they might not be fundamental. They might not be the real bedrock of the universe. The big idea now is that space-time is what we call emergent. Here's a good way to think about it. Take temperature. A single solitary atom doesn't have a temperature. The concept is meaningless. Temperature is something that emerges from the jiggling motion of trillions of atoms altogether. Well, in the same way, the smooth fabric of space and the constant flow of time could just be an illusion, an emergent property of something much, much deeper. So what is this deeper reality made of? Right now, the leading idea points to one of the weirdest things in all of physics, quantum entanglement. You know, what Einstein called spooky action at a distance. The theory is that at its most basic level, the universe isn't made of space or time. It's a vast network of quantum information. And the feeling of moving through space, the experience of time passing, that's just a reflection of the connections, the entanglement within this deeper network. And figuring this all out, uniting gravity and quantum mechanics, that's the holy grail. It's the biggest quest in physics today. And as Brian Cox puts it so well, black holes aren't just some weird cosmic oddity. They're the testing ground. They are the place where our old theories fail, forcing us to come up with something new and better. They are our only real guide into this deeper level of reality, our only window into a true quantum theory of gravity. You know, in the end, this whole journey into the heart of a black hole is really about what Einstein said science is for. By pulling and pulling on this one loose thread, this one paradox, physicists are hoping to get just a little peek at what's really going on underneath it all, at the deeply hidden structure of reality. And it just goes to show you, sometimes the darkest, most mysterious things in the universe are the ones that can shed the most light on everything.